All right. So I'm recording this on my new laptop. That's why the microphone sound is probably a little echoey. But I was just talking to someone on Twitter about FPGA design tools, and one thing I haven't really shown on stream is that over the last 6 months, I've spent a good amount of time in my free time learning FPGA design and doing a bunch of sort of prototyping work along those lines. And so I've gotten a little bit familiar with how that works. And I remember the first few times I tried to use Vivado, which is Xilinx's FPGA design suite. I did find it quite overwhelming. But in hindsight, um, a lot of that confusion was preventable. It's not, I mean, it is a very deep and complex tool, but I think if someone shows you a walkthrough sort of live, a lot of it becomes, comprehensible rather, and you can kind of then start to dig in yourself into the details. So I thought I would do that. I thought I would basically do a really simple demo project, starting from scratch, kind of walking through the design flow and showing a bunch of nooks and crannies that I wish someone had shown me when I was looking for tutorials on this stuff 6 to 8 months ago. So let's just jump in. I guess first up, it's worth noting that Vivado is free, at least in this edition. So if you want, after going through an annoying registration process and license setup process, you can get a copy of this yourself for free from the Xilinx website. But after setting up the licenses and stuff, when you open it, you get this screen. And so we're just going to create a new project. And I'm just going to call it counter. And these settings are fine. And then you have to select what board you're targeting. So we just pick some Arctic board with not too many gates. This looks good. And that's enough. All right, so this is the main screen in Vivado. Right now we don't really have anything, and there is a ton of stuff here, and we're only seeing a fraction. And I will try to talk through it as we proceed. So I'm not really going to talk too much about Verilog and HDLs and hardware design languages, or description languages rather. I'm just going to assume that you can kind of intuit from the code I'm about to write what it does, but it's obviously important to note that you're not really programming a computer per se, you're really describing hardware. So keep that in mind, but I won't go into too much detail otherwise. So first thing we have to do is add a source file for design for RTL code. So a lot of this stuff is pretty tedious, a lot of dialogues. So let's call that counter.sv versus Verilog. Just get these defaults. That's fine. All right. So it generates a stupid file with the timescale definition. It's probably fine, and an empty module. So we're going to create a counter for an 8-bit quantity. And so this is a clocked synchronous circuit, which means we need at least 2 inputs. We need a clock input and a reset input to set it up initially. And so let me just write out the code. So we create an 8-bit register. We set this combinational value to be the incremented value of the current register value, and then we have an always block, which is responsible for basically latching the next value for this count register. And so if reset is asserted, and this is a synchronous reset, then we want to set the count to 0. Otherwise, we set it to the the next signal. And I'm actually going to intentionally make some bugs, and those were bugs that I actually did when I did a drive run of this earlier, but I thought they were illustrative, so I'm going to more or less do it in the same order and show you the bugs, and since this is stuff you're going to run into yourself if you ever try to do this. So this is a nice or simple functional block. Right now it doesn't really expose any outputs from this counter, which you probably would want in practice, but for now let's just say we do this, so it's purely there's purely inputs. We have to create a top module, which just represents our design as a whole. I'm just going to call it main. And this thing will get, will have clock and reset pins as well, because these will then come from off-chip. So there will be a clock signal coming from off-chip and a reset signal coming from off-chip, either from power on reset or a manual reset button or something like that. And so this main module will instantiate the counter, and that's it. So you can see you saw it reorganize itself up here. It correctly infers that main is the top level module for the design. So I'm already going to tell you that there's a bug here. But let's see what happens. So the first thing you do is go to the whole process of RTL development is this sort of multi-stage process of going through different compilation stages. What is called elaboration is kind of the first level of compilation. Okay. So what you basically see here is a schematic of what it compiled. So the job of the front-end compiler that's part of this elaboration is to essentially take your high-level source code and generate net lists, which are sets of cells that represent sort of abstract blocks, and then the nets that connect them. So this is sort of an abstract schematic circuit. In this case, you can see it lists these two top-level input wires, nets, and it has this block, but it seems to be empty. So basically what has happened, and that's the bug I referred to, is that even though the elaboration stage doesn't do a crap load of optimization, one thing it will do is do dead code elimination effectively. And so in a case like this, it can detect that even though we have this internal state, the state is actually not being exported anywhere to the outside world through the pins, top-level pins. And so it just decides, hey, I can get rid of all of it. So basically it ends up doing dead code elimination on the entire counter, even though we're instantiating it. So that's a bug. So we are going to fix that by exporting the count. Did I make a typo? Oh, yeah. Well. Let's create a separate wire for that. And then here we have to route it through. Let me just call it out. And let's rerun the front-end compiler. Let's see if we get something more useful. And we did. So you can see now, aside from having more than two nets, indeed it has these nets for the bits of the counter for the output. This module here, this block, is now also actually non-empty. So if you click the plus button, you get this internal exploded view. And this is sort of like assembly code, like machine-independent assembly code, I guess, for what the compiler generated. So it instantiated a register with 8 bits. You can see how it sort of stacks up a bunch of these schematically. You can see the external clock pin is routed to the clock pin of this flip-flop. And you can see the D, which specifies the next state of that register on the rising edge of the clock, comes from this adder. And so basically it took, the high-level code we wrote saying we want to do this add, and it instantiated this high-level, addition operation, and wired up one of the inputs to a constant, which is 1 because it's an increment, and the other operand comes from the Q, which is the output from the same register. So this is, you can see this feedback loop represents the fact that it's, it's a feedback system, it's a stateful system, and then the output also gets routed to the external output pins. So yeah, this looks good so far. And there's some other stuff here we're not going to go into. So next step is synthesis. This is a more in-depth, hardware-specific compilation phase. It's given the actually I don't know if it runs on the elaborated netlist or directly on the source code, because sometimes these are by different vendors. But in any case, you should think of this as doing more, as you'll see, doing more vendor-specific, device-specific, hardware-specific compilation. So if you can see we've got more nets, we've got a bunch of more stuff. If we go to the schematic for this is the same block we were looking at before, but now we're looking at it in the synthesized version. And remember, before we had, we just had this abstract register and an abstract adder. And now it's actually generated much more granular hardware-specific representations of what was going on there. So you have these FDREs, which are flip-flops, individual bits flip-flops. You can see each of these has 4 input pins and 1 output pin. This is the clock pin with that notch, and the CE is chip enable. So this is basically just sort of an overall functionality, an overall gate for whether to latch or not. There's D, which is the next value, and there's also a specialized reset input, and then Q is the same as before. That's just the output. And then for if you look at the structure itself, what is it doing? Let's go look at the bits in order. So the lowest bit first. First off, you can see all the chip enables are tied off to a constant. So you can see this over here is called const1. So basically, this chip enable is tied off to 1, meaning logically this thing is always on. There's no gating going on. And the clock should come from the external clock signal. Oh yeah, here, which comes in here. So this is the shared clock net. And D comes from the output of this lookup table, a LUT1. So it's a lookup table that takes 1 input, produces 1 output. So let's see whether this makes sense or not. The lowest bit of a counter behaves in a very simple way, right? It just alternates the bit. And so it only needs to know the previous state to produce the new state of that single bit. So probably what this is doing, and we can check, is that it's just a simple inverter. And so if you select it and go to the cell properties and go to the truth table tab, you can see that indeed I0, which is the first input, when that is 0, then the output is 1 and vice versa. 1 goes to 0. So this is a simple inverter. And so based on that, and given that this specifies the new value of the the first bit of the counter, you'd expect the input here to be, the previous bit 0 or previously significant bit. And indeed, that's what is going on. I'll explain this schematic notation. Even though these FDREs are actually individual bits, there's this way where you can kind of gang them up together into a conceptual vector of them. So that's what this fat line with the triangle and the indices means. It basically means that, the Q of this top one, count reg 0, becomes the, index 0 of this vector net, and so on. And then on the input side, you can see this one selects the 0 component and feeds it in. So indeed, this does the inverter. And given that, you can also understand how the other bits are expressed by the synthesis compiler. The count 1 is a function of the 0 bit and the 1 bit. So you'll note that these are not using a sort of ripple carry cascaded configuration. They're actually, the LUTs for the higher bits are actually looking at all the lower bits in order to make a decision. Except you can see for these higher bits where the LUTs are not big enough to sort of have enough inputs. And so at that point, it ends up having to cascade them in order to, you can see it has a big LUT 6 and then it cascades them into two smaller LUTs in order to produce those count reg 6 and count reg 7 bits. So anyway, this is sort of the idea. So you can see that, well, if you know anything about FPGAs, you know that the main logic element, fine-grained logic element, is this kind of lookup table, and that's what these things represent. So anyway, so now you can see we're still at a schematic level. It's not laid out yet, but we're now dealing with primitives that are native to the hardware platform. So let's proceed to the final stage, which is implementation. And you can see in the upper right corner, it's doing the asynchronous execution of that. And it's going to take a while. And you might note all of these steps are taking quite a while, even though this counter code is pretty much the simplest possible thing you can imagine. So up design is design optimization. So it's trying to, just like a source code compiler is trying to do kind of logic optimization basically at this phase. Then it does placement, or place and route, or route now here. So placement is basically figuring out where to place these different blocks that it's generated, and then routing is figuring out how to do the routing between them and in a way that satisfies all the constraints and optimizes for time and area and all these other things. All right, so it's going to take a while, but once it's done, we'll be able to see what took place. All right, open design. All right, so we have the same netlist hierarchy over here on the top left, but now we have a so-called floor plan view. And the floor plan is a, not 100% true to life, but representative, fairly representative picture of the actual device you're targeting and where things are laid out. So, before we look at our specific code and how it was mapped onto this thing, let me just talk a little bit about the high level sort of 10,000 foot view of this thing. So you can think of this as representing the actual die, right? It sort of is trying to represent that. You can see it's divided into these square tiles. Within these tiles, you have a bunch of repeating structure. You basically have all the I/O pins and buffers on the side. These are the color-coded things along the left and right edge. Then internally, you have a bunch of repetitive structure. Let me just zoom in here as an example. You have these blocks here. Let me just zoom in further. You have these blocks here. You have this big unit of two, sort of a pair of twins, or not a pair of twins, a pair, which is called a CLB, a configurable logic block. And each of those is divided into two slices, usually called slice L and slice R. I guess not too important to go into the details, but I do want to sort of give you a brief inventory of what's within each of these slices. There are, on the left, you have 4 lookup tables. So I was talking before about lookup tables. Well, there is this lookup table that can be configured basically in 2 basic different ways. it has up to 6 inputs. If you take 6 inputs, then it will only have one output, which is this 06. But it can also be configured as a unit with 5 inputs and 2 outputs. So it has some flexibility there. The lookup table is essentially programmed at startup or at reconfiguration time, which is sort of not something you do dynamically typically, but it is possible to do some things dynamically. But essentially, you should think of these being almost like EPROMs or something that are hard-coded at config time. And then after that point, they can do these operations really quick where you feed the inputs and it generates the corresponding output. And can represent any possible function with 6-bit inputs and 1-bit output, or 5-bit inputs and 2-bit outputs. Beyond that, you have some other functionality here. You have this mux, which I'm not going to go into too much detail, but basically you can control how some of these things are routed. There's also this thing can select between the output of this thing and the input, another external input and some stuff. Then there's this thing here called the carry chain. You can't see the internal connectivity, but this basically goes bottom to top, and it's sort of an efficient way of implementing ripple carry adders, but can also be hacked to do things that are not quite ripple carry adders. And then finally, you have a bank of flip-flops here on the right. So this is where the flip-flops are. These are all identical, and there's 8 of them, as I think you can see. So there's 8 flip-flops here. So that's the basic logic element in one of these 7 series Xilinx FPGAs. Beyond that, there's a bunch of other resources on this chip. The big one are these so-called BRAMs, block RAMs, which are a fast SRAM. And I don't know how much BRAM this thing has on chip, but it probably, it's quite common for these things to have a few megabytes of SRAM, or BRAM as it's called, of BRAM on the die. You can see that there's the red ones over here, and I think over here you have another fixed function block. You can see it has the same basic footprint, at least in the schematic view, but it's not BRAM, it's actually DSP, so this is a 48-bit multiplier, sort of hard-coded multiplier, so you don't have to implement that yourself out of LUTs and stuff and carry chains. So aside from that, there's a bunch of stuff with I/O buffers and FIFOs for dealing with I/O and all this other stuff over here. But that was just like the quick overview. Let's now look at what the optimizer and the place and route did with our code. So it's down here. I'm just going to zoom in. So just going to zoom in. So you can see these things that are like cyan or whatever that color is. These are basically the ones that are occupied. If you click one, you can see the corresponding cell or net in the net list. One thing that's very useful for understanding what's going on is Control-T, which you can also find in the right-click menu. It's show connectivity. If you do Control-T recursively, it's going to generate the sort of the connectivity, the recursive connectivity, at n levels away. So if I click Control-T again, it's going to figure out the ones that are connected to that, and then so on. And you can see eventually here we have these lines that go way off the screen because they're connecting to the outside world with I/O pins. So anyway, that's very useful for understanding the connectivity. Let's look at these things a little bit more. So previously we were looking at the synthesized design in the schematic view, and we got kind of an idea of how things were done with LUTs. As it turns out, that's basically how it ended up mapping onto the actual physical resources in the end. Let's try to find, so we have a LUT1 here, mapped onto a LUT6 because that's what it has. But if you look at this thing here, God, I do hate the zooming in this program. If you look at this thing here and click this, as before, when we were looking at it schematically, we can go and look at the truth table. We can confirm this is indeed an inverter. Let me zoom in a little bit more. One thing that's a little bit annoying in this floor plan view is that, God, stop it. If you click Control-T in this thing, you can see where the output goes, which is the new. We can confirm this is the new count red 0. But annoyingly, we know the input has to be the old bit 0, so it's the Q output here. But if you do Control T, it doesn't draw a line over there. But you can see that if you do Control T again, it is going to select it over here, but it's not going to draw the line. So it's a little bit confusing. You can also select this input pin. You can see the populated input pin is highlighted. So if you select this manually and do Control T, first it selects the net, because it's the pin, then the net, and then whatever is connected to the net. So you can see, in this case, it actually does the right thing. I think you can do it here. If I look at this Q, yeah, well, it's a little hard to see. But anyway, you'll have to trust me that even though they don't visualize it very well, this internal block connectivity is actually there. So the output of this goes to this, and the Q in this goes to that. So this is like the 1-bit counter. And similarly for this, let's see, this is count 1. You can see, oops, as before, this is the truth table. It takes 2 inputs and has 1 output. You can see that there's 2 populated input pins. If we do Control T, it will show the output, and then we'll select both of these 2 as inputs, which is that right? No, it's actually not right. Well, it's because there's no way to fine-tune how it's doing the connectivity search. But anyway, yeah, that's in the ballpark. So okay, so now we actually have this thing mapped onto physical chip. Let me just do this again and show you where the I/O pins got placed. So the I/O pins were inferred from the fact that our top-level module had, if you recall, it had a 1-input, a 1-bit clock, a 1-bit reset, and then 8-bit output. These are all mapped over here onto. You can see this is the reset. So there's an input buffer and iBuff. So basically these are like taking external chip signals off chip and sort of amplifying them and forwarding them. And here you can see all the different. These are OBuffs, so these are external drivers really. So if you take one of these and you can see what is it? There's an OBuff here, and then there's a pad, and the pad represents the actual physical pin. And yeah, I don't know why it's not. Yeah, so anyway, you can see the recursive connectivity here. All right. So one thing we haven't actually. So the next thing we want to do is get on top of the timing. Now, this is a very simple circuit, but there's still limits to how fast we can clock it. So right now we haven't really described to the system which of the, well, we've used the CLK clock line in a way that sort of implies that it's a clock, but we haven't really told the system about the clock. The clock is going to be, in reality, it's going to be an off-chip oscillator of some sort, like a crystal with an oscillator. And so, it's not like hard-coded into the FPGA chip, like what frequency it's going to oscillate at. It's going to be driven off-chip. And then internally, it has PLLs and other kinds of voltage controls oscillators that try to keep, multiply up or down the frequency and keep phase lock and all this other stuff. But ultimately, the signal originates off-chip. So we have the pin, but we have to tell it something about that pin so it can do timing analysis. So for that, we're going to need timing constraints. So let's go to that now. So we go to the synthesis section and go to edit timing constraints. And there's a bunch of different kind of timing constraints and you can set up here, but we just need a primary clock constraint for now. So we had our object called CLK. You can see it defaults to a period of 10 nanoseconds. So this means 1 nanosecond would be like 1 gigahertz. So 10 nanoseconds is 100 megahertz. And you can see relative to the period, here are the rise and fall times. So this is like a symmetric square wave clock. Basically, there's no kind of 75%, 25% duty cycle, anything weird. So this is just box standard, and we will implicit search. I think this is fine. All right. So it generated a clock. I just want to go to the project manager and show you where that ended up. So we created our original design source file. Wait, didn't it generate that? Usually it generates an XCC file. Hang on. Oh, here we go. Let's call it main.xtc. So now we have this represented in a constraint file. This file is actually just a tickle command file, so this is not as declarative as it looks. Well, it's both more and less declarative than it looks, I suppose. But for now, we'll just let it generate this code for us. But you can see it just basically says what we entered in the wizard earlier. So yeah. So now we've expressed the period, and now we should be able to do some sort of timing analysis, because we said, this is the clock, it runs at this rate, and it's connected to this pin. So now the system should be able to do some sort of timing analysis. So let's try that. So we go to the report timing summary in the synthesis view. I'm trying to remember if we have to give it any special data. I don't think so. Yeah, let's just use the default settings. All right. So it generated a timing report from the synthesized design. This is not the place design. Let's actually do the place design, because when you do a timing analysis based purely on the synthesized design, it doesn't actually know where everything is going to end up exactly on the chip, which can have pretty significant consequences, obviously. So maybe let's do timing analysis based on the placed and routed design, not just the synthesized design. Is out of date. Guess we have to rerun it. By the way, when I'm doing my own RTL programming, I don't spend any time, if I can help it, inside this program. First off, a lot of these steps, as long as you're not doing anything involving this kind of graphical stuff, you can do it from the command line or the command prompt. So all these tools are available from the command line. Although you usually have to write some tickle code in order to string them together, but that's fine. But even beyond that, like the tools themselves, even in tickle mode or in command line mode, are not great. I do tend to use different workflows. It doesn't require me to run all these slow steps all the time, because as you can see, even for a trivial design like this, it really kills iteration time. Yeah, so in my projects, I've been using an open source compiler called Verilator, which generates C++ code that represents a cycle accurate emulation of the code. It can have issues, especially like it's not a perfect replacement for a full sort of flow like this, but for a lot of the basic kind of programming and design stuff, it's more than sufficient. You can simulate quite complicated chips at a fairly high simulated clock rate. Like full systems on a chip, you can maybe simulate at 100 kilohertz or something, which is enough to do boot up and sort of trace testing and stuff like that on real chips. So it's very convenient, even if it's not a perfect litmus test for whether it's going to work in hardware. All right, so we re-ran implementation. Let's go and look at the timing summary here. There are no user-specified clock constraints. Why does it say no clock? I see. I screwed up something with the constraint, I think. What did I call clock reset? maybe this is it. So, no, it's still not working. Let's just see here. I had this working in my dry runs. I assume I just did something bad. Register lat pins with no clock, driven by root clock pin. Maybe I made a typo in my code. Let's see. Counter instance count reg C. C is the clock. So it's not something in the code. Oh, I guess I have to rerun implementation since I changed the XDC file. Let's see if this works better now. I should also look at the message log to see whether there are any warnings. But yeah, spent a lot of time waiting around. You can see what it does here. Technology mapping. Where was that? All right. Well, here we go. I don't know why this is so much slower. I could have sworn it wasn't this slow the first time, or previous times. Maybe the clock is actually working and that's why. All right. All right, this looks like it actually is correct now. It has the timing slack and everything. But let's just make sure. Right, so this actually works. So let me explain this timing view, and some of these warnings should be gone now. Yep, the no clock warning is gone or error. So you have here this design timing summary. So remember we set a clock period of 10 nanoseconds, which you can see up here as well. The system is trying to ensure that there aren't any critical paths from flip-flop output to flip-flop input, which take longer to propagate and settle than the clock period. And it's also taken into account off-chip delays and stuff like that, or trying to anyway. And so that's what the slack is about. In this case, we have 10 nanoseconds, and the worst negative slack, which is a good thing, is 8.2. So basically what that means is we have roughly in theory, we could run this rather than 10 nanosecond period. We could run it at something like 1.7 nanoseconds. So it could run much faster if it was only for this anyway. There may be some other stuff. That's a really high rate for this FPGA. I don't know if that's actually feasible. But so this is basically because we have a very simple circuit, right? So that's what that means. You can go and look at, what is the thing I'm thinking of here? You can go and look at the paths, like, where is it? Maybe I didn't specify it. Yeah, maximum number of paths for group. Display paths with slack less than. Okay, I think it's because all these paths are so fast it's not displaying. It's not actually displaying here. But anyway, if you have any paths that are close to being not good enough to hit their timing constraints, then they will list them in order to sort of like, here are the things you should be worried about, or try to rearrange if you want to meet the constraint. But anyway, so yeah, so now we've imposed this clock constraint. I want to show you something interesting that may surprise you, but it's totally explainable. Let's go to the floor plan again. So we still have our little thing down here. Oops. But something seems to have changed. If you pay attention. Before. This looks different. So it's actually changed the design and how it's laid out and synthesized based on the timing constraint. So do you remember previously the basic design was to use a lot of LUTs, in fact at least one for every counter bit, with a lot of inputs for each of these LUTs, all the previous lower bits. And basically what it's decided is that now we've actually given it its deadline, the timing constraint it has to meet. It starts using the slack to do more area efficient optimization. So previously it was using a ton of LUTs and I think three slices total. Now it's using only one LUT, and it's using these adder chains that I mentioned, or the carry chains internally. Now these are a little bit slower because there's propagation delay. There's a carry chain that goes all the way from the lowest bit all the way to the highest bit if you have a long, if the value of the register is like 11111 and you do an increment, then there's a carry ripple all the way from the lowest bit to the highest bit. But it doesn't really care, because if it meets the timing constraint, great, then that gives us space to optimize for area like it did here. Let's see what this LUT actually does. This is, well, let's see. LUT. Why is it not? Where is the cell properties? Okay, there we go. So what is the truth table? Okay, so this is just the inverter truth table. It's feeding, I see. So this is probably just injecting, the kind of the alternating thing, and then it's propagating through. It's like a ripple counter or something like that. Anyway, so yeah, you can see how, even though we didn't change any code, by actually specifying timing constraints, it reorganized how it generated the design. So that's pretty cool. Okay, what was the next thing I wanted to show? Right, this is obviously a very trivial design. And you can see in this case, it decided to place these things kind of near the left edge because, let me just take a random thing, because that's where, that's the nearest it could get basically to the clock pins and whatnot. You do have the ability to constrain things physically if you want to lay out certain submodules in different locations. So I just thought I'd quickly show that. In this case, we only really have one interesting module. There's the top module, but it just contains the counter module. So let's just take this module and let's do floor planning, draw P block. And suppose we wanted to be very specific about our layout, and we did something like this. And so it deleted that block because now the design is invalid, it has to regenerate it. But we basically now added a constraint that this block has to be laid out within this so-called P block. P stands for physical. So let's try to rerun implementation and see what that does. This is really useful if you, well, this thing specifically has its limits, but basically you can use this to do absolute placement of like big blocks. You typically don't want to use this for super fine-grained submodule placement because one of the issues is that P-blocks are absolutely positioned, and so they're very specific to exactly how you've laid things out. There's something called relatively placed macros, or in Vivado, which is an older feature, or a newer feature called XDC macros, which are basically a way of taking of specifying sort of relative placement constraints between submodule blocks, like Xilinx, for example, in a way where you can reposition them without kind of destroying the constraint, but kind of still having this notion that, hey, I want to place this block near a block RAM, or hey, I want the ALU to be right next to the bank of registers. So you can kind of do some constraints and then have the compiler figure out, the placement route system rather, figure out the nitty-gritty details of exactly how to lay things out within those constraints. So, God, this is taking long. Yeah, this is, like I said, just for a simple counter. So slow. By the way, we ignored some of these timing check complaints. What it's complaining about here with the no output delay and no input delay. Output delay, there's 8 warnings because there's 8 output pins for the counter. And one for I guess this is the reset pin, probably, not the clock pin. Basically, it wants to know the delays of any external pins so that if you have any kind of late arriving things that are still synchronous to a clock, it can use that in its timing analysis to check for timing violations and also through that to drive placement. So if you have a late arriving signal, you can put stuff that depends on it closer to that pin, so there's less routing delay, and hence you have more ability to meet that timing constraint. But we don't need that for this example. All right, so we just reloaded this. We will just reload it. Let's see if it actually met our P-block constraint. I believe it did. So you can see here, it now placed stuff within the block, but still to the leftmost edge because it wants to be close to stuff. If we rerun our timing report, we should see, maybe the delay isn't noticeably longer, but let's check. Yeah, so it looks like this is already updated. Okay, I guess the distance is not a big issue for this. What the heck is this? Oh, it's just a graphics board. But anyway, all right, so that's P-blocks. You can imagine doing this for kind of major, the P-block stuff is generally only something you want to do for sort of big, chunky placement, like you're instantiating like a big IP block and you want to say, hey, put it here near these pins. You don't want to use this for super fine-grained stuff, like I said, because it's too brittle, basically, with respect to changes. Changes both with respect to the source code and also the device you're targeting. All right. I'm not going to demonstrate XDC macros because I haven't prepared that, so I made too many mistakes. But anyway, XDC macros is a way you can do, like I said, you can organize like a macro of modules that you can, or cells you can instantiate with a certain relative placement. You can kind of then translate them around and kind of have them kind of snap to nearest relative to the constraints. So if you want to place something next to BRAM with an XDC macro, you can then sort of instantiate the macro, slide it around, and it will sort of snap to nearest relative to the features it wants to be close to where you're trying to place it. All right. What else did I want to show? Don't think I want to go into this other stuff. Yeah, let's talk about simulation. At this point, in theory, if we had an FPGA board and all this, and we're using the right pin mapping so that the clock and reset actually go where they should, then we could download a bit stream to an FPGA and go test it. I do have FPGAs around, but I haven't set them up for testing, so I'm not going to show that right now. And if you don't have an FPGA at home, you wouldn't be able to do that yourself either if you're following along. Let me go into simulation, though, just as a final note. So like I said earlier, when I'm doing kind of development and testing, I don't spend any time in this at all. I generally use Verilator and do all my simulation that way, if I can get away with it, and I generally can. But it does have a simulation flow that you can use. So in order to simulate, you actually need to have a test bench. So I'm going to add a source file with a simple test bench. Looks good to me. All right, so this test bench is not going to have any input pins because it's not actually going to be connected. You know, it's not going to run on a physical piece of hardware. It's essentially just a way of instantiating our main module and sort of stimulating it with, you know, kind of simulated clock reset stimuli, and then visualizing the traces of what actually happens to its outputs over time. So Verilog and VHDL started their life actually as simulation languages. So if anything, this stuff is their bread and butter. It has a lot of stuff for doing kind of coroutine style parallel tasks that are running kind of synchronously interlocked with delays and whatnot. So yeah, that's what I'm gonna show a simple example of that here. All right. So first thing is we have to instantiate the main module, and so you know it needs some variables for that. For out, that's this much, and then we have an initial block. The whole notion of initial only makes sense in a simulation context typically, because it's all about, like, you know, if you want to do things like resets in RTL code, you have to manually do the stuff we did in our counter, like, you know, if reset, then set the state to something. But in simulation, it's nice just to be able to say, hey, when the simulation starts, run this code in sequential order. Sorry. So the first thing we have to do is reset the chip. I did a synchronous reset, which arguably is not the correct way to do it, but let's just go with it. Depends on what you're trying to do. On FPGAs, synchronous resets are more common, I suppose. So if you note a reset logic here, it looks for the reset value being high on the positive edge of the clock. So anyway, very first thing, let's set these pin to known values, and then let's have a unit delay, and the unit delay is relative to the time scale up here. So 1 means 1 nanosecond. And in our chip, we are going to, this simulation, by the way, doesn't really use all the timing constraints. So you can just do it in internally consistent units that don't necessarily have to relate to the real clocked rate, just a note. So 1 nanosecond is pretty standard for that. So we reset it, and then we wait 1 cycle, or 1 nanosecond, not 1 cycle. And actually, let me just bring reset high, and then we're going to do this. And going to go high with that. And then we're going to have a loop where we basically just alternate the clock at one nanosecond intervals. Sometimes when you're doing, let's see here. So I'm just going to simulate, I mean, sort of akin to a real system. I'm going to just do it this way. I'm just going to simulate basically setting the reset high and then running the clock for 10 cycles, and then setting the reset low, and then running the clock for real. Now not reset, so it's not going to just reset to the same state, but actually hopefully going to count. So I think that's it. So the first thing we're going to do is the so-called behavioral simulation, which is just running on the elaborated design. So if you remember from the elaborated design, it's operating at a fairly high level in terms of, instantiating adder nodes and stuff like that, not like LUTs. Okay, so this does not appear to be working. Oh, it is. 0B is hex. Right. So you can see here, out starts out an indeterminate value. This red X thing means X is a value in Verilog that anything can take, I guess, except a few special types. And when you're doing simulation, X stands for like an unknown value, something that hasn't been initialized typically, or represents indeterminate state or something. So you can see we don't set the clock initially. That's why initially, not until the, So we start with reset asserted high, and then we do a bunch of cycles. And you can see on the rising edge, the first rising edge after reset is high, the default value 0 gets latched into the output register. And then even though it's doing a bunch of cycles, this thing is not changing. And then we deassert reset, but to continue cycling for 10 cycles. And you can see this register goes through 10 values and then holds its final value because we stopped clocking it. And you can see, if you want to look at the individual bits, you can see the typical, periodic pattern of the bits of a counter. So this is a behavioral simulation. This is running on the, this is running against the net list of the elaborated design. So let me just remind you of what that looks like. That was this thing here, which is very coarse. So it has a vector register and has a feedback loop with a simple adder, just an abstract adder. So that's what the behavioral simulation is running against. Basically what it's doing is it's taking the Verilog code here that you wrote for the test bench, and it's taking whatever the net list represented in Verilog form for a given compilation passes, probably after optimization and so on for some of the later passes, and it's running it against this code. So you typically, for basic functionality, it's good to start with behavioral, but you want to use some of the later phases in order to actually capture any logic optimization that may have changed behavior. Okay, let's try to do a post-synthesis simulation. And if you don't do your reset correctly and stuff like that, so you can see this is not doing anything. I mean, the clock is changing, but so you can see reset goes high. We do a bunch of clocks. It does reset to 0, but then it never seems to really change its value. Okay. Let's see why that is. It could be because its post-synthesis actually is taking into account the clock constraints. There would be an easy way to test that, which is just to change these to 5s. I don't normally use these simulation tools, so I may be a little bit off with some of this. Alright, so this one worked. So that was it. Basically, I guess it wants to use the real, the real clock values. So it does sort of set up hold analysis potentially, I guess, since it's doing timing simulation. But anyway, you can see this is going through the values 1, 2, 3, 4, and so on. And we can do the same against the post-implementation, which is after it's done. all the final design optimization, tech mapping. And yeah, you can see this one works too. So this is just a trace, and that, I believe that was the final part of the tool I wanted to show. This was definitely not exhaustive. And in particular, there's a very cool debugging feature when you're running on hardware where it has a logic analyzer, sort of virtual logic analyzer, you can use to do a lot of cool cool features that are reminiscent of software debugging by instantiating actual FPGA code and sampling signals and buffering them and doing triggers and stuff like that. But without hardware setup, I can't really demonstrate that. But yeah, I think this showed some of the basic stuff. So just to reiterate, we created a simple counter module. We created a top-level module to instantiate that. We did a elaboration run to look at the schematic. We did a synthesis run. Then we added timing constraints. We did a full implementation run, looked at how things were laid out, the different logic elements on the chip, how they relate to the high-level design, how adding the timing constraint changed what chip resources were actually synthesized in response to our high-level code. The whole timing slack thing. And I guess finally a quick overview of the simulation and how to write a dumb test bench and how to get it to work for different kinds of netlist simulation. So yeah, that's pretty much what I wanted to cover. This is obviously extremely superficial, and if you've never looked at anything like this before, most of it may not have made sense. But hopefully, if you want to go and poke around in Vivado, you now have some handholds that you can kind of grab and go from there. So that's it.